Okay, guys, just a heads up, I'm going to record this for a couple different reasons, for different purposes. So if anybody doesn't want to be recorded, I don't know that it's actually going to pick up anybody. It might just be here. If you guys are worried, maybe I'll have you sign releases after. I just really want to remind myself how fat I've gotten, so I want to look at this video afterwards and just get disgusted. Yeah. What's that? It is, yeah. It picks up this beacon, which is also a mic, so it sounds really good. Okay, so let's get right to it. I just want to remind you of something that we haven't talked about in a very long time. If you have a function, the net change in that function is just simply the difference in the outputs from where you stop minus where you started. Okay, so the net change from A to B of a function is just f of b minus f of a. All right? Now, the reason I wanted to remind you of that is because that's actually part of the second of the two big questions that we had at the very first day of class, and actually they're on your syllabus as well. So the two big calculus questions. It's actually kind of a nice point to just sort of catch your breath and see, okay, yeah, we've made some progress in these big questions. So the first question is, given a quantity that's changing, and we'll call it f of x, how fast is it changing? That was the big question number one. And now that's automatic for us, right? The answer is, well, if you want to know how fast, take the derivative. The derivative tells you the rate of change, right? So we've spent the past few months figuring that out. Look at f prime of x. That's how you get the rate of change. If you have a quantity that's changing, you describe it with a function, its derivative tells you how fast it's changing. Okay, so sort of like, yeah, check that off. We got it. Question number one answered. Question number two, if you remember, was given the rate of change of a quantity. So I'm gonna write it as, just to make it really clear, if you're given a derivative of some function, and someone asks you how much, here, I'll underline it this way so it stays, the structure is the same. How fast was the first one? How much will the quantity change? So in other words, i.e., what is f of b minus f of a? How much, or really, what's the net change in the quantity? Does that make sense? I mean, no, does it make sense? Is it ringing a bell? I guess what I should say. So let's try to see what we can bring to bear in this problem. Anybody have any suggestions as to what we might do if someone gives you a derivative, f prime, and then asks you to figure out f of b minus f of a? What should you do? Anybody have an idea? I give you this, and I want you to give me this. So what do you have to do? Raj?
Take the antiderivative of f prime of x first.
Okay, so take the antiderivative of f prime, which would be f. And then once you have f, just throw in the numbers, right? Throw in a, throw in b, subtract. Find the difference between them. So here, come over here. Find the antiderivative f of x, and then compute f of b minus f of a. That's it. So it's nice to see these two guys right next to each other because, all right, I give you f and ask for how fast. Well, okay, the derivative. This one's saying, here's f, get f prime to answer the question. This one is, here's f prime. So to answer the how much, you got to come back up to f with the antiderivative, Raj. Good suggestion. And then compute f of b minus f of a. Once you got f, it's like everybody can throw in numbers, right? And just get the output. Okay. So here, before we get too far, I was going to give you a little bit of history, like to contextualize like how these problems were thought about. But before we do, let me just give you a specific example instead of like abstractly just talking about it. We were doing this all the time on Wednesday with the acceleration, velocity, and position, right? We were doing antiderivatives to get information. Raj?
So, looking at this and looking at the homework,
Yeah.
number 26 is somewhat similar. It gives us a domain for f prime of x.
Mm-hmm.
And it gives us f of b minus f of a with a domain,
Mm-hmm.
restriction in other words. It tells us to find the f of x equation. Is it possible to find f of x equation if you don't even have an actual output for f prime of x?
Yeah, I guess, I mean, the way you said the question, evidently, right? It seems like there must be. Yeah. I don't know. I actually can't follow the question as you asked it. Maybe let's look at it after.
Okay.
Here, given the velocity of an object, let's say it's v of t equals t squared plus sine of t feet per second. Sorry, x squared. Let's do x squared minus. Sorry, minus sine of t. Sorry about that. Doesn't matter in a big way. So I want to point out, it doesn't sound like it, but they're actually giving us a derivative, right? The velocity is a derivative. So it's kind of this, given a rate of change. Well, velocity is a rate of change function. What is the net change in the object's position from t equals 0 to t equals 3 seconds? Okay. Do you see this as a specific example of the second question, second big calculus question? Okay. They're giving us the rate of change of position, velocity, and asking us for the net change in the position over a certain time span. So let's do it. Pete, can you tell us what we should do? How are we going to get that net change in position?
Find the antiderivative of v of t.
Okay, so if v of t equals t squared minus sine of t, what's p of t going to be? Then position, let's call it p of t, sorry. All right, so what is it, Pete? Can you give us the antiderivative?
T cubed over 3 minus cosine of t
Minus cosine of t
plus c.
plus c. Okay, let's take a look. Anybody have any comments, things to add, things to question, anything at all? Hussein? The suggestion is maybe make this plus cosine of t. Can you say why, Hussein? Because if we start with positive cosine, the derivative will end up as negative cosine. So that negative will actually come from in here. So does that sound okay, Pete, to tweak that? Good. Now, Pete also told us plus c, and that was excellent that he remembered to do that. We always encounter that, right, with the antiderivative. Did they give us enough information to find what c is? Remember on Wednesday, they always had to give us an input and an output for us to figure that out? And I don't see any of that. But if you just hang on for a second, I think it's not going to matter. I think it's going to be okay. Let's check this out. Now, we can compute the net change from 0 to 3 in the position. So P of 3 minus P of 0. That's what we want to, maybe I should label that. The net change in position equals P of 3 minus P of 0. Where was it, or where will it be in 3 seconds minus where was it at 0 seconds? And we can just throw it in. So 27 over 3, that's 9, plus cosine of 3, plus C, minus, and then if we throw in 0, we'll get 0 plus cosine of 0 is 1 plus C. I'm just putting the number into both parts. Let me do it like this. And let's see, this is 9 plus cosine of 3 plus C minus 1 minus C. Subtracting that off. And here's why that C is not going to be an issue. It's going to drop out right now. If you think about it, that makes sense. If you're interested in a difference, it doesn't matter if you add the same number to both of the minuend and the subtrahend. Those are the two names of the pieces that are being subtracted. If you add the same number to them, the difference stays the same. So the C's are kind of irrelevant. The difference remains intact. So this is 8 plus cosine of 3. Cosine of 3 is about 0.9-ish, maybe even like 0.99-ish. It's pretty close to negative 0.99. So this is going to be about 7 feet. This is the exact answer, and this is just an estimate for us. Okay? I should say this. I got an email from the calculus course coordinator about the final exam, because it's coming up. It's about a month away. She mentioned to me to remind you guys that if you can give an exact answer, you should. So this would be the answer they would be looking for on the final. If you want to estimate for your own purposes, that's okay. But they want this, not this. Okay? All right. Any questions or comments on that? All right. Now here's what I'd like to do. This actually is pretty special that these two big questions are really just the flip of one another. But that's not how people saw them. That's not how people tried to answer them. I mean, these problems have been around for thousands of years, like 4,000 years before anybody noticed that they were related in such a smooth way like we have here. So people didn't just say, all right, we got these two questions. Well, let's go after this one first, like we did in our class. So we did one thing, the derivative, and then said, okay, now let's look at going backwards, and it turns out it's this question. They tried to answer them in parallel. So that's sort of what I want to try to do with you in the next couple days, just sort of show you how you do this without this, without antiderivatives. So how would you handle it if you either couldn't find the antiderivative or you didn't know what an antiderivative was? So we're going to play it. So I'm going to ask you to forget for a second. You'll remember it later. But forget antiderivatives for the moment, and let's see how this works. Okay?
Why can't we use mean value theorem?
Good question. So let me throw it to you. How would you use mean value theorem on this?
Like we know the mean prime, if it's continuous and differentiable, then it would be mean value theorem.
Mm-hmm.
So we know that it equals f of b minus.
Oh, let me just say one thing. I don't know if you could hear in, but she said if you've got a differentiable function, then you said it like if you got a differentiable function, then it's the mean value theorem. That's kind of how you said it? Yeah. If it's differentiable, it's automatically continuous, right? Well, it doesn't mean just because, so I'm just clarifying something. It doesn't mean that because you have a differentiable function that this is a mean value theorem problem. What it means is that the mean value theorem applies here if you wanted to use it. It's kind of like it's on the table. But like, for example, so's the intermediate value theorem, so's a whole bunch of other facts that we could bring to bear. So I know it's just kind of like it's in your mind, right? Because you just have worked on homework and stuff on it. It's like, oh, that the mean value theorem works here. That's what you could think, but it doesn't mean that this is a mean value theorem problem. Okay? It's like it's in the toolbox. Doesn't mean you're gonna go to it. But go ahead. What were you thinking? How are you thinking to involve it?
I was just thinking like p squared minus sine t would be on like the derivative side, f prime of c.
Yeah.
Then equals f of b minus f of a over b minus a. And we already have a and b.
Okay. So here. I'm sorry. I was trying to put my head around it. What is f of 3 and f of 0?
And that's what we're trying to find.
Right.
Minus f of a. So that would be the numerator part that we're trying to find. And our bottom is b minus a. So that would be 3 minus
Be 3. Yeah, that's 3 in the bottom. So then what's on the derivative side?
the t squared minus sine of t.
At c, right? At some c value. Do you know what that is? No. The mean value theorem, you either need to know the average rate of change, be able to compute it, get a number, and then you can say, oh, the derivative is going to be that. Or you need to know the derivative, and then you say that average rate of change is going to be that at that, at some point. The problem is we don't have either one of those. There's unknowns in both sides of it. It's not a bad thought. Because it does, in fact, now I really see why you're thinking of the mean value theorem, because it's got that change in the outputs. She saw this, what we wanted, right? And then said, oh, wait, but if you just add this, now that's like that's the average rate of change. That's kind of leading her to think, well, that means the derivative of p prime, also known as velocity, has to be that. The problem is we don't know this and we don't know this, so we can't use it. We got too many unknowns. So how do we address it? Well, we go make the p function, so get the antiderivative and plug in. Right? She was thinking, can we use this information to help us figure out this? And it's a great thought. I can really see that now. The problem is we don't know that number. All right, so let's do this. Let's pretend, just for a second. So here's a question. Let me say it this way. But what if we couldn't find the antiderivative? Let's say the velocity function that they gave us was just so incredibly messy that we couldn't find the antiderivative. We just couldn't do it. Or, so that's a real thing. We talked about that on Wednesday. Going backwards is actually really hard. Or, so this is just a, so this is real. This is real. That's a real question. Or, what if you didn't know? About antiderivatives. So this is just an exercise, because you guys do know about antiderivatives, but I'm going to ask you to play along. Like, let's pretend for a second that we don't even know what an antiderivative is. Okay? In the middle of next week, we'll remember. We'll bring it back. You should remember it on the weekend, too, because that's the homework. So just forget it for right now. Remember it in a bit, and then we'll forget it again Monday. All right, so here's an example. At your job, your pay rate, hopefully after this class for the rest of your life, every time you hear the word rate, your brain should say, oh, derivative. Okay, so they're giving you a derivative, or this story is about to give you a derivative. At your job, your pay rate is $15 an hour. Here, let me write it this way. $15 per hour. How much money do you make if you work 10 hours? Oh man, and it's recorded too. I just screwed up. This is perfect. I wanted to refer back to the questions. This is question number 2, the guy that was right here, right? They're giving you the rate of change of something, and this is weird to think of it this way, but it's the rate of change of your wealth, right? It's the rate of change of how much money's in your pocket. Every hour, the money in your pocket goes up by 15 bucks. Okay, $15 per hour. And then they're saying, how much money will you have in your pocket if you work 10 hours? So the net change. What's the change in your wealth going to be? Does that sound reasonable? Okay, now, you guys have all answered it, right? Let's just check. So what's the answer?
150.
Okay, so did everybody get 150? $150, right? How'd you do it?
I just multiplied 10 by 8.
Okay, so how much money is 15? You took 15 times 10. So this is the rate times the time. And that's $150. All right, so nobody did calculus on this, right? Did anybody do calculus on this? You can, if you want to. Why is it so easy? Can anybody pinpoint like what makes this problem so easy? What about it is making it so easy? Good. The thing that makes this really super simple is that the pay rate is constant. That's really what makes it easy. So we should take note of that. This is easy because the pay rate, I'll say it that way, the pay rate is constant. It never changes. It's just 15 bucks per hour every single moment you're working, okay? So let me offer up a new job, probably a better job. New job, new pay rate. Let's say it's $10 an hour for first 4 hours. Then it jumps to $15 an hour for next, let's say, 8 hours. And then it's $30 an hour. Oh, you know what? We make this 10 hours. Sorry, for the next 10 hours. And $30 an hour for any time after that. So here's the question. How much do you make if you work 20 hours? All right, well, you guys just take 2 minutes, just at your desk by yourself, figure out what you do to answer this, and then we'll come back and check. All right? Oh, sorry. I need waivers. Wait. So you guys are all on camera. So see me after for a waiver. Okay, let's check in. Jarrett, can you share with us what you're thinking, like how you're computing? What'd you get first of all?
I don't know if it's right. I got 490.
$490. Anybody else get 490? Ooh, is it too high? Too low? Too low? Oh, it's higher than yours? Okay.
I would have just multiplied 7 times 4 and then added it to 15 times 10 or 30 times 10.
Oh.
I know that that's not right. I just did it to look first.
Okay. No, there's actually good stuff in there. That was a great idea. Why did you do 10 times 4?
With the first 4 hours.
Okay. And then the second part you said was
Next 10 hours.
15 times 10. All right, so I see what she's doing. See if this fits with what you were doing. It seems like she's taking that 20-hour time interval and she's breaking it up. Is that what you guys did? Into 3 pieces? Okay, good. I want to point out, so Jared, this is what she started to do is exactly the right thing to do. She's taking, because the rate is not constant. It changes. So her idea is a perfect one. Break up the time interval, which is 0 to 20, into pieces. By the way, I should say this. You might look at this and say, man, this is really overcomplicating this example. The reason I'm doing it, the reason I'm being so formal with it, is it's going to help us when this problem gets even harder. So if you just look at what Jared did here in a more formal way, it's going to translate to our next step up in difficulty. So it's like, that's super easy over there. Okay, this is a little tougher, but the idea that Jared gives to us is going to work, and then we'll see how it plays out the next level. Okay? Into pieces, and here's the key point, on which the rate is constant. That's crucial. So she didn't just split it up into any old pieces. She split it up into 4 hours, the first 4 hours, the next 10 hours, so from 4 to 14, and then the last one, not 10, that's where the extra came from, 6 hours. Okay? It's not bad to try it, see if it goes, if it shows up in your check or not. But you only work 6 hours at that rate. So right here on this one, on this first subinterval, the pay rate is $10 per hour, right? On this interval right here. On this second subinterval, the rate is $15 per hour. And then on this subinterval, the rate is $30 per hour. And now we can do it. It's just like 3 little mini problems. So the net change in your wealth, or how much money you make, net change in your money, I don't know how to say it, how much you make, is 10 times 4. Rate times time, just like over there. Plus, and then there's a little extra bit of money here. Rate times 10. Is everyone comfortable where the 10's coming from? I mean, you can see it in the description, but it's also here, right? 14 minus 4 is just 10. And then $30 per hour, that rate, times the time length here. 20 minus 14 is 6. That's it. You just add up these little bits of change. So it's a sum of bits of change. Each one of these is a little bit of money, a little bit of change. So let's see. 40 plus 150 plus 180. 330, $370. Is that what you guys got? All right. So I'll stop here, but I'll just ask this question that we'll return to on Monday. What happens if the rate doesn't just change a couple times, but what if the rate is always changing? Like at every single moment, from moment to moment, it's something different. That's where we're going to go next. Okay?